Hello, my name is Anthony Hazapis and I will be presenting the work done by Forth in Greece and IBM Research in Ireland to build what we call a unified storage layer for supporting distributed workflows in Kubernetes. Let's begin from our motivation so it's easier to understand the problem we are trying to solve. Our groups have been cooperating in the context of Evolve, a Horizon 2020 European project that aims to build a consolidated platform which supports high-performance data analytics workflows running on HPC hardware to handle the needs of processing extreme-scale data. The goal is to combine big data frameworks that provide scalability, HPC infrastructure for performance, and cloud services for their portability and ease of use, and show the applicability of the end platform through real-life applications. Evolve includes 7 pilots and a supplementary set of more than 20 proof of concepts covering a wide spectrum of industrial and academic use cases. Traditionally, HPDA applications fall into one of 2 categories. They are either implemented using specialized code, like MPI, running bare metal on dedicated equipment, or use some big data framework like Spark, which can scale out in VMs or containers in the cloud. Early on, we decided that our best approach is to use Kubernetes as the execution environment and containerize both HPC applications and big data frameworks. Kubernetes abstracts the hardware resources, which allows us to replace and scale the hardware independently of the software stack. It also allows us to seamlessly exploit hardware-specific HPC features available in nodes like the InfiniBand network or accelerators. Using containers enables us to unify both approaches and run different software stacks as part of the same overall workflow. Applications running in Evolve are written as complex graphs that run some containerized code as part of each graph node. These workflows are created, configured, and triggered from notebooks that also set the stage for execution, collect results, and present visualizations. It is not uncommon for an application to use a combination of different frameworks and microservices like Spark, Dask, TensorFlow, Kafka, MPI, and others. Well, this approach does solve the issue of gluing together different and diverse stages of computation, but what about storage? It turns out that every different software stack has different, sometimes conflicting assumptions about how data should be stored and accessed. Typically, HPC applications require the presence of a shared file system with the same paths available to all instances running in parallel. On the other hand, big data frameworks, which are mostly tailored for the cloud, may use object stores like Amazon's S3. Our workflow orchestration framework, Argo, refers to data exchange between steps as artifacts and includes plugins to manage their movement between stages, but copying in data as part of every step and then copying the results out proved to be inconvenient, not to say frustrating, and required very specific configuration of storage attachments, which is contradicting to our requirement of portability. So ideally, we would like a storage abstraction that provides separation of storage configuration and workflow definition, so developers can write portable applications with configurable storage attachments selected on runtime, depending on the execution environment, the placement of data, or other parameters. It should also provide transparent access to different storage solutions to allow workflows to benefit from many different current and future storage services. And of course, simplicity and ease of use to boost productivity and make the whole system more friendly. These were the requirements that led us to the design and implementation of the USL. USL introduces the dataset abstraction, which is stored in Kubernetes as a custom resource definition, or CRD. Each dataset includes a type and configuration about the respective storage endpoint. For example, a dataset can refer to an NFS folder, a local or remote S3 bucket, or an H3 bucket, which we will talk about later on. Datasets are understood by the USL core, which in the simple case creates a corresponding mount point for each inside the user's containers. This way, users can write portable workflows where containerized applications work with local files. Where these files will be stored is decided on runtime, depending on the configuration of the respective datasets. The same workflow with no changes can run with different datasets if necessary. Now let's see how this is achieved. USL consists of 3 main components that run as services inside Kubernetes. Carved-Dash, the front end, which provides a web-based interface for users to set up their datasets. DataShim, which is the core engine that creates the corresponding volumes for each dataset in Kubernetes and mounts the volumes in containers, and H3, which is an object store that provides the actual storage service, or to say this better, the USL native storage service, as USL supports many storage services. H3 supports multiple interfaces. It can be embedded into applications or accessed through a dataset and acts as the unified storage offering in USL, as well as a storage gateway to high-performance key-value stores. The figure on the right shows an overview of all the components. Each component can also function autonomously in any Kubernetes deployment, but they have all been designed and implemented together with the overall integration in mind. Also note that all components are open source and available in GitHub. In the following slides, we will present each component in detail. Carvdash implements a platform frontend. It provides a landing page for users working on the platform. Through its web-based interface, users can launch pre-configured services or applications. These deployments are based on configurable templates, so the users can also create their own in order to extend the available collection. For each service launched, Carvdash provides an external secure URL to connect and make sure that the respective containers are run in separate namespaces, one per user. Carvdash also provides a simple interface to manage containers residing in a private image registry and offers an API for executing any of the above actions through a notebook. As shown in the figure, the first step of developing an application in the platform is going through the login process in the dashboard, which includes setting up datasets and launching a notebook server and workflow controller. Then, the user will switch over to the notebook to write workflows and launch them. The dashboard's top-level screens include the datasets and files tabs. Datasets is used to define and manage USL datasets, while files provides a familiar web-based interface for two special datasets that are configured by default, private and shared. These two datasets are automatically mounted in all containers at /private and /shared. Private holds the user's private files, while shared is a single file collection shared between all users and is meant for sharing large datasets. The next USL component is DataShim, the core engine of USL. DataShim monitors datasets and manages the life cycle of corresponding volumes by configuring the appropriate CSI plugin in Kubernetes. CSI stands for Container Storage Interface and defines a standard API for creating and attaching volumes in container-based engines. There are CSI plugins for many different storage implementations. DataShim currently supports H3, NFS, and S3 datasets by using the respective CSI plugins. It also supports mounting the contents of tar.gz archives as folders, and just recently we added a mechanism for local caching of remote datasets. The details are in the DataShim website. Let's just mention here that we create an internal dataset that caches a remote one using a local Ceph deployment. The whole caching scheme is transparently handled by DataShim. The user just selects whether caching is enabled or not. DataShim commonly creates a volume for each dataset and includes a mechanism to automatically mount it in selected pods. However, optionally, DataShim may inject the dataset configuration into a pod as environmental variables instead of creating a volume. The life cycle of a dataset starts when a new dataset CRD is created. Then, the DataShim controller converts the dataset definition to a persistent volume and persistent volume claim in Kubernetes, which are in turn handled by the appropriate CSI plugin. Having set up the volumes in Kubernetes, users can now reference them in their pods. To make this even easier, DataShim monitors specific labels in pod definitions, shown here as dataset.0.id, and if they are found, automatically adds the necessary configuration to mount the volumes. In the example of the figure, the user creates an H3 dataset, which results in an H3 volume supported by a bucket in actual storage. Then, the user submits a workflow consisting of several containers, which are annotated with the appropriate labels for DataShim to automatically mount the corresponding H3 volume. And that's it. All volume-related stuff is handled internally by DataShim. The third USL component is H3, an object storage service. Object stores represent a cloud-native approach to storage, and most applications running in the cloud use object stores in one way or another. They have become popular because they practically offer unlimited capacity with no storage management requirements to applications. But what happens when you have cloud applications you want to run locally? There are solutions, but they are lacking in performance or features. We have rethought the concept of the object store in an HPC setting and present a new approach, an object store embedded in the application backed by a high-performance key-value store. You can think of H3 as a translation layer for key-value operations. We support various key-value engines as well as a local file system. Of course, if you choose to run H3 with a local storage backend, then the whole stack runs locally with no network traffic. In all other cases, we will practically move the object service close to the application and let the storage backend handle the network. The key-value API is generally simpler and faster. Specific key-value implementations may also use the high-speed networks and RDMA for transferring data. As expected, evaluation results indicate that the H3 approach especially favors the latency of small-sized data operations. The figure shows the internal structure of H3 and its various components. The core of H3 is a C library called H3lib, but we also provide Python and Java wrappers. On the back end, H3 supports several key-value stores like Redis, RocksDB, and Crayon, while on the front end, we support several interfaces for compatibility with existing software that cannot be changed. H3 Fuse implements the file system, while S3 Proxy provides an S3 compatible service. Our H3 CSI plugin uses H3 Fuse for mounting H3 as a volume in containers. This is an example of how H3 objects are translated into key values in the backend. Here, the user chooses the Python API to create a bucket and an object. Note that in the backend, we create one key for the user, one for the bucket, and one for the object's metadata, while the object's data is split up by H3 into many key value pairs depending on its size. A table showing which keys are used internally by H3 for object data and metadata is included in the paper. This is now an example showing the integration of all USL components. All services are running in containers, carved as DataSim H3 embedded in the CSI H3 deployment, as well as Argo, the workflow controller, and some key value store like Redis. First, the user logs into the dashboard and creates an H3 dataset using the Redis service, which is stored in Kubernetes as a dataset CRD instance. Then, a workflow is submitted through Argo, which triggers the deployment of a pod as part of some step. This request is intercepted by Carvdas as it refers to a container running in the user's namespace. Carvdas adds the user's datasets as labels in the pod definition. Then, DataSim intervenes as there is now a dataset label. DataSim has already prepared the appropriate volume definition in Kubernetes and now attaches it to the pod. Assuming no other controllers intercept the call to create the pod, it's now up to Kubernetes to decide where to run it. In this example, Kubernetes selects the second node, but the pod now contains an H3 volume definition, so it contacts the CSI H3 controller to ask for a mount point for the volume. The controller contracts the node plugin that runs at the same node as the pod to handle the mount. And as a result, the node plugin creates an H3 bucket at the endpoint provided and uses H3 Fuse to mount it. Note that the key value store here runs in another server. Redis will provide a key value interface backed by local memory, but we could use some other key value store with a network API. So a new volume is created. Actually, Fuse runs in the CSI H3 node plugin container, but the mount point is propagated to the host so it can be shared among containers running in the same machine. Finally, the workflow step can start with the H3 Fuse volume attached to the specific folder. This looks like a complicated process, but it really is simple once you break it down to the individual steps. Note that the user only creates a dataset and launches a workflow. All the rest happens automatically and almost instantaneously by the USL. The point is that the workflow relies on the existence of the mount point, and its type is defined by the dataset. The same workflow can then run again without changes, using, for example, an S3 bucket hosted in the cloud. So to sum up, We expect the current trend of containerizing different software frameworks to become the established way of running workflows in the following years. Containers provide portability and allow moving between local installations in the cloud, as well as between development platforms and HPC hardware. This paradigm shift demands new abstractions to cope with storage heterogeneity. Our unified storage layer is a step in this direction. With the USL, developers separate workflow programming from configuration of storage attachments, which enhances the portability aspect. The USL provides the full stack from a user-friendly front end to a high-performance backend. Also, we should note again that all three USL components are distinct, separate open-source projects that can be used individually and on any Kubernetes installation. The USL is the combination of these three components running together. USL has been developed to support the needs of the European Evolve project, which it successfully does, and constantly receives very positive feedback from its users. Here are the GitHub links for the different USL components. For more information on the Evolve project, you can visit evolve-h2020.eu. Thank you very much.